Hey there, I had a question about problem 26 in section 3.3, and I thought I would talk through it for everyone who might be interested. Um, so here we have a differential equation with some parameter a, some positive real number parameter a. If you go through and solve this thing, you get essentially damped oscillations. I'm not going to solve it for you, but you get essentially an exponential times trig functions. And the exponential has a negative exponent, so we have decaying oscillations. And so roughly speaking, it looks like this, right? Oops, I don't know why that disappeared. There we go. So then in the second part, it says if you set a equals to 1 or a equal 1, you're going to get a specific exponential, a specific set of trig functions, but you're still going to have this decaying oscillation. And the question is find the smallest t so that the absolute value of the solution is less than 1/10 for t bigger than t. So what you're trying to do, and let's just pretend that this is 0.1 here, and I'll just sketch through a horizontal, and maybe this is negative 0.1. Oops, switch back to black here. And I'll sketch in those two. What this question is really asking is, how long does it take, how long does it take for the oscillations to have amplitude less than 1/10? What's the capital T where this solution enters that range and stays there forever after? And you can kind of see how this works. If I made that smaller, if I pinched this little range together so that maybe it was 0.05, negative 0.05, this capital T would go further out. Or if these oscillations started out higher, they would take a longer time to kind of settle down into this range. So that's the idea here. If I'm trying to answer this question, there are mathematical tools that kind of help me find this thing exactly. I can just use a numerical solver and figure out where this point is. I would probably plot it, I would get an estimate, and then use a numerical solver to really narrow down. That's not necessary here. Just estimate it, plot it, and use the graph to estimate the t value where this happens, where the damped oscillation enters this range and stays in it forever after. And then it says repeat part B for 1/4, 1/2, and 2. So you change this number. We tried it with 1. Now try it with 1/4 and 1/2 and 2. And you're just solving this equation each time with a different value for A. When you solve it each time, you get a different damped oscillation, right? Maybe the amplitude's a little bit higher when the A is 2, and so it takes a little bit longer to enter in. So this T value, where the damped oscillation enters this red band, is going to change depending on what this parameter A is. Do the same thing, solve the equation, plot it, estimate what this capital T value is for each of these, and then just plot 4 ordered pairs, right? The A value and the capital T value for 1, the A value and the capital T value for 1/4, and so on. And this will shed a little bit of light on the effect of this parameter A on, in other words, how quickly this thing decays, how quickly this thing enters that range. And that's basically it.